In the ever-advancing field of physics, the Large Hadron Collider plays a crucial role. In a recent groundbreaking development, scientists have reported a first-time discovery. Imagine the heart-pounding joy as scientist uncovers a new secret of the universe when a ghostly particle reveals itself in the depths of the Large Hadron Collider. So, what is this hidden treasure and why is it being kept secret? The term Large Hadron Collider might seem unfamiliar to some. However, given its giant scale and potential, its discoveries hold immense implications that could affect the entire universe. Nestled within a 17-mile circular tunnel underneath the Swiss terrain, this colossal instrument played a crucial role in identifying an unseen particle. The construction of the LHC, a billion-dollar project, took place at the European Laboratory of Particle Physics, also known as CERN, located in Switzerland. To paint a clearer picture, the LHC is the world's most substantial and powerful particle accelerator. This marvelous piece of engineering comprises a 27-kilometer ring of superconducting magnets and accelerating structures designed to boost the energy of particles. The primary purpose of the LHC is to answer unresolved queries in particle physics, as described by the Standard Model. The Large Hadron Collider is a place where scientists conduct experiments to understand more about the universe. It has different parts called detectors, like ATLAS, CMS, ALICE, and LHCb. Some detectors look at general things while others focus on specific phenomena. The LHC had its first operational period from 2010 to 2012, called Run 1. After that, it took a break for maintenance and upgrades, which is known as the long shutdown phase. After a 3-year break, the LHC started its Run 3 in 2022. There are plans to upgrade the LHC to the high luminosity LHC by 2029. This upgrade will increase the amount of data collected by 10 times, allowing scientists to study the lesser-known mechanisms in more detail and discover rare phenomena. One key contributor to this ambitious project is Professor Anders Ritt, a physicist at Cornell University. Involved in the CMS experiment since 2005, Professor Ritt has contributed significantly to commissioning the CMS pixel detector and the search for supersymmetry in Higgs physics. He also actively participated in developing new detectors for the CMS upgrades, especially the track trigger. These ambitious projects aim to probe the properties of the Higgs boson further and uncover new physics processes. However, this ambition comes with its own set of challenges. These include surviving the harsh radiation environment, achieving greater granularity in detectors, and efficient event selection, also known as triggering. So what exactly is the LHC and why do it exist? In simpler terms, it's a colossal machine designed to create and control super high-energy subatomic particles. Scientists can then study the interactions of these particles. Essentially, the LHC offers a platform for researchers to test and confirm theoretical predictions. For example, it can recreate conditions similar to those that occurred a billionth of a second after the Big Bang. Such conditions have not naturally occurred in the universe since that seminal event. The LHC has thus become an integral tool in modern scientific research, often playing a key role in studies involving subatomic particles. Recently, it was announced that for the first time, ghost-like particles, also known as neutrinos, were discovered using an atom smasher. Neutrinos have long fascinated scientists due to their elusive nature, and the discovery has given researchers brand new ways to investigate the microscopic world, pushing us closer to understanding their role in the cosmos. Neutrinos may be hard to detect, but they're actually quite common throughout the universe. For instance, while you're viewing this, around 100 billion neutrinos are passing through each and every square centimeter of your body. But you probably don't feel a thing because these microscopic particles, which originate from various sources such as stars, supernova explosions, and cosmic rays and radioactive decay, have no mass or electrical charge. They're almost as light as a feather, weighing just a tiny fraction of an electron. These ghost-like particles travel at almost the speed of light and seldom interact with matter. This elusive nature has led to their ghostly comparison. However, catching neutrinos is not an impossible task, it just requires a lot of effort. Early successful attempts to detect neutrinos were made in the 2000s through various experiments such as the Antarctic Ice Cube Detector, the Japanese Super Kamikokande Detector, and the Mini Boon Detector at Fermilab. These studies relied on a method known as Cherenkov radiation to indirectly detect neutrinos. The Cherenkov method works similarly to how a sonic boom is produced when an airplane surpasses the speed of sound. In this case, a faint blue glow is created when a particle traveling at light speed passes through a medium, like water, that slows down light. This glow is of great interest to scientists. However, this technique only captures neutrino signatures as they pass through the Earth from the Sun and does not allow for the study of direct collisions between neutrinos and atomic nuclei. For example, it cannot explain the nature of high-energy neutrinos observed in particle accelerators like the LHC. Due to its design, the LHC is incapable of directly detecting neutrinos. Its structure uses magnets to guide particles along a circular path towards collision, with detectors placed strategically at intervals. These magnetic signals do not influence neutrinos and other charge-free particles and therefore bypass the detective's field of view. To address this issue, scientists from the Phaser collaboration developed a new neutrino detection method called Phaser NU. The Phaser NU mechanism uses heavy metal plates made of lead and tungsten. Between these plates, layers of light-detecting emulsion are sandwiched. For detection to occur, neutrinos first collide with atomic nuclei on the metal plates, creating particle byproducts. These byproducts then interact with the emulsion, leaving behind imprints of their paths. The resulting particle trails, once analyzed, allow researchers to confirm that neutrinos indeed produced some of the marks. They even differentiated between the three known types of neutrinos, known as flavors: tau, muon, and electron. Phaser Nu is a considerable advancement compared to its predecessors. For example, with the Super Kamiokande requiring 50,000 tons of water, Phaser Nu weighs in at just 29 kilograms and is built from recycled materials from CERN. Additionally, Phaser Nu is sensitive enough to distinguish between the rare tau neutrinos and the more common muon and electron neutrinos, as well as differentiate neutrinos from their oppositely charged counterparts, antineutrinos. Despite these advancements, many fundamental questions about neutrinos remain unanswered. For instance, the exact differences between neutrinos and antineutrinos is not clear still. However, with tools like Phaser Nu, scientists are inching closer to finding these answers. The team behind Phaser Nu has committed to spending the entire year of 2022 hunting and capturing 10,000 neutrinos. The knowledge gleaned from these studies could shed light on the origins of matter and the pervasive presence of dark matter in our universe. In this pursuit of knowledge, researchers are turning to unexpected sources. They are studying tree rings for signs of past supernovae, demonstrating the connection between terrestrial life and celestial events. The death of a star, typically a spectacular explosion, showers the universe with intense bursts of gamma radiation for years. Despite the multitude of stars, such supernova explosions are exceedingly rare. Observations suggest that in our Milky Way galaxy we might witness 1 to 3 supernovas every century. Although the most recent one occurred over 400 years ago. Hence, this innovative approach to studying tree rings for evidence of past stellar deaths is another example of the intriguing lengths scientists go to understand our universe better. It was this machine that made the discovery of the Higgs boson, a particle that's key to understanding why things have mass. Now, it is set its sights on something more mysterious: neutrinos. But what are neutrinos? Well, think of them as tiny ghost particles. They are so small and move so quickly that they can pass through just about anything without interacting with it. In fact, again, while you're reading this, there are billions of them passing through you, or at least probably. We know about these particles thanks to a variety of experiments, many of which are quite large and complex. These experiments have shown us that neutrinos come in 3 different types, or flavors. But there's still a lot we don't know about them. For example, we don't know why there are more particles than antimatter particles in the universe. It's one of the biggest mysteries in physics. Some scientists think that neutrinos could hold the answer to that question. In addition to neutrinos, the scientists at the LHC are also investigating other mysteries of the universe. For example, they are studying tree rings to learn more about supernovae or exploding stars. Imagine a big fireworks show that's like a supernova, a huge explosion that happens when a star blows up. It's so bright that it can light up a whole galaxy for a little while. This explosion also sends out special light rays that can travel all the way to our planet Earth. These light rays can change the amount of special kinds of carbon, called carbon-14, in our air. Now, think about trees. As they grow, they take in carbon from the air and they store it in their rings, like sipping a fizzy drink through a straw. When we look at tree rings, we can see how much carbon-14 was in the air when the tree was growing. A group of scientists, led by a man named Robert Breckenridge, have been looking at tree rings to learn about supernovas. They found that 4 big star explosions, or supernovas, happened in the last 15,000 years, and were close enough to change the carbon-14 in our trees. The scientists saw that there was more carbon-14 in the tree rings when the supernovas happened. It's like finding the fizz in your drink has gotten a little stronger, showing that the tree sucked up the carbon-14 that the supernovas made. By doing this, they can learn so much more about these big star explosions and how they change things here on Earth. This can help us understand more about our universe and its history. The LHC and its team of scientists are making incredible discoveries that are helping us understand the universe. Whether they're studying ghostly neutrinos or the fiery deaths of stars, their research is pushing the boundaries of our knowledge and bringing us closer to understanding the mysteries of the cosmos. The Atlas, a majestic piece of scientific equipment spanning approximately 148 feet in length and reaching about 82 feet in height, has been instrumental in unveiling the secrets of the universe, including the discovery of the Higgs boson. This colossal machine which weighs about twice as much as Paris's Eiffel Tower and is half the size of the majestic Notre Dame Cathedral, offers invaluable insights into the cosmos' mysteries. ATLAS, along with other significant detectors such as ALICE, CMS, and LHCb, is used by curious researchers worldwide to find traces of elusive phenomena like dark matter and extra dimensions. These elements are concepts often associated with the realm of science fiction, but these scientists are actually turning them into a science reality, so do with that what you will. Both the ATLAS and CMS were primarily assigned the mission of unearthing the Higgs boson, each one being part of unique experiments conducted at the Large Hadron Collider and managed by a global group of dedicated scientists. The actual operation of the LHC is a feat of its own. Imagine two atoms colliding at speeds rivaling that of light. The resulting collision creates an eruption of data, telling tales about the atom's structure and the forces that bind them. The LHC can orchestrate a staggering 600 million particle collisions every second. The data unleashed from these collisions is a treasure trove of knowledge, but there is a catch. Due to the sheer volume, it's impossible to record all the data. The ATLAS, for instance, churns out data at a rate that would overflow 100,000 CDs every single second. However, only a small fraction of this data can be retained, around 27 CDs worth every minute. Once the data is captured, scientists conduct a process known as reconstruction. They cross-examine their theoretical models of particle behavior with the actual collision data, comparing virtual crashes on a computer simulator with real ones. The difference between the two could hint at the discovery of new scientific insights. Every single day, this process grapples with approximately 1 petabyte of data, which, to put into context, we would need 223,000 DVDs for storage of. The task of uncovering new scientific knowledge is daunting, especially when it involves sifting through a staggering 30 petabytes of data every year. Adding to this challenge, physicists at Imperial have facilitated a new range of experiments at the LHC, which make the production of monopoles more likely. Despite no monopoles have been discovered yet, these new experiments provide scientists a clearer picture of what they should be seeking. In 2018, the LHC managed to force lead nuclei to collide, creating heavy ions. These conditions were considered favorable for the production of monopoles. If these lead nuclei narrowly missed each other or merely grazed past, a striking event could occur. A magnetic field is generated up to 1 million times stronger than that of neutron stars. These fleeting magnetic fields only last nanoseconds, but provide an exciting avenue for magnetic monopoles. One aspect central to this theory involves the production of electrons, and then their antimatter counterparts, positrons, often regarded as the electrical world's monopoles. The group's investigations didn't lead to the discovery of monopoles, but they did uncover something intriguing: a split in Earth's magnetic field, likely caused by the sun's radiation, which persisted for nearly 14 hours. This phenomenon, known as the coronal irregular region, is a large-scale plasma structure formed in the heliosphere's low and middle latitude regions, due to the interaction of solar wind streams. Like coronal mass ejections, CIRs, when launched towards Earth, can cause severe space weather due to their potential shock waves and compressed magnetic fields. Larger CMEs can disrupt space weather conditions, leading to intensified geomagnetic storms, which can cause fascinating visual spectacles like auroras. However, large CMEs can also disrupt technology. For instance, the Carrington event in 1859 had a significant impact on the worldwide telegraph system, where sparks from telegraph machines ignited papers and risked operators' safety. CMEs also can lead to widespread blackouts by overlooking the power grid due to electrical current surges. They can interfere with radio signals, increasing static in the ionosphere, and cause global positioning systems coordinates to drift by tens of feet. The intricacies of the universe continue to absolutely amaze, astonish, and astound us with each discovery. We continue our journey of understanding the cosmos' mysteries. Gosh, communication satellites, especially those dwelling in high geosynchronous orbits, are particularly susceptible to coronal mass ejections. CMEs can cause substantial damage to these satellites in numerous ways, including through direct collision or penetration by high-energy particles. These celestial disturbances can, in severe cases, lead to significant financial losses. For example, just last year, a geomagnetic storm, triggered by a CME, wiped out about 40 of SpaceX's Starlink satellites. The estimated cost for this catastrophe soared above $50 million, marking a significant blow for the space exploration company. Earth is generally less likely to be affected by solar storms in February. This is because our planet is safeguarded by a protected magnetic field that shields us from their impacts. Earlier, it was believed that these shields opened and closed rapidly, but recent research has brought new understanding. Scientists now recognize that our protected magnetic shield isn't as impenetrable as once thought. It's similar to a sturdy house that keeps out most of the storm, but will still allow raindrops to leak onto your comfortable couch. While the magnetic shield absorbs the lion's share of the energy from space storms, Some does manage to slip through, leading to potential disruption in our satellites, radio transmissions, and even electrical grids. As we move closer to July 2025, the Sun is anticipated to step into its most active phase of the solar cycle. Despite being relatively early in the cycle, the Sun is already exhibiting signs of increased activity, which implies that your chances of observing the Northern Lights or the Aurora Borealis over the next 3 years might escalate from being just excellent to extraordinarily good. Given these insights, expressing concern about potential changes in Earth's magnetic field is natural. The disappearance of our magnetic shield could trigger catastrophic scenarios, the most chilling of which is the potential depletion of our breathable air due to the solar wind. The solar wind's natural force is potent enough to strip an entire planet's atmosphere until nothing is left, as likely happened with Mars. Mars, believed to have once boasted a water-rich environment and a thick atmosphere similar to Earth, lost its protective magnetic field billions of years ago, resulting in its atmosphere being gradually swept into space. Without the shield, only atmospheric pressure plummeted and water began to evaporate, only to be whisked away by the solar wind. If Earth were to lose its magnetic field, it's plausible that our atmosphere, our oceans, all life on our planet might share the same fate. Moreover, the potential vanishing of Earth's magnetic field would have severe repercussions for animal life, even before the atmosphere is entirely lost. Various animals, from birds and sea turtles to lobsters, honeybees, and even fruit flies, rely on Earth's magnetic field for navigation. They possess magnetic receptors, akin to built-in compasses, that guide them in their migratory patterns or help locate their nests or hives. If Earth's magnetic field goes away, many animals would get lost. This might cause their numbers to drop, and in some cases, could even lead to some species disappearing completely. Hence, the significance of Earth's magnetic field extends far beyond our immediate perception, having profound impacts on technology, the environment, and all life forms inhabiting our planet. That's why it's paramount we continue to study and understand it to ensure the future sustainability of Earth and its diverse ecosystems. What's the one thing about the LHC that really blows your mind? And what future discoveries do you think that they're going to unravel? Let us know in the comments and make sure to hit that like button. Your support really does make a difference. I know, everyone asks, but it does. So, also don't forget to subscribe to stay updated on more. And that's about all I got for you, so later.